integers, floats, OCaml, runtime, C, assembly. These are the keywords for this video. Now, more coherently, the plan for the video is to have a deeper dive into how numbers are represented in OCaml. Browse some relevant pieces of OCaml runtime source code to support our findings, run some benchmarks, disassemble some programs, and find out what sort of overhead we can expect from this universal representation of values in OCaml. Without further ado, let's roll. Hi all, my name is Artyom, and in this video I want to talk about numbers in OCaml, which is this basic thing that we don't usually think much about or care much about until we have to. If you don't know much about how values are represented in OCaml, you may want to have a look at this chapter of real-world OCaml, which is excellent. It describes this subject and not just for numbers, but also different kinds of values like structures and variants and so on and so forth. So definitely take a look. What I want to do in this video, though, is to take just ints and floats and go a bit further down to the metal, have a look at what sort of assembly will be generated when we're dealing with different types of numbers, and also what kind of overheads we can expect compared to unboxed numbers as we have them in C, let's say. All right, so let's switch to the editor and start with something simple. Let's say this particular snippet of code, let x equal 42. If we execute it, we see that x has type int. Now, let's try to dissect this value a little bit. Okay, 42 here. So we will use these methods from module obj that provide different types of information about a particular value. For instance, in this particular snippet, we will ask 3 questions: whether something is a block, how many words are reachable from the value, and the values tag. So if we run it for the int, we will see that int is not a block. There are 0 words reachable from this particular value, and the tag is 1000. In OCaml, there are several types of ints. One is just int. Another one, for instance, is int64. If we do the same thing for int64, we will see that int6442 is a block. There are 3 words reachable from this value, and it has a tag of 255. To kind of make a bit more sense out of this, it is worth having a closer look at the runtime source. Our entry point into the world of OCaml values is this header, mlvalues.h, which sits under runtime caml. It has a bunch of definitions, like what is a word, what is a long, what is a value, block, field, etc., etc. But the gist is, all OCaml values are the size of a word, which is 8 bytes and 64-bit architecture. So like one number. And this number is either a pointer to some value in the heap, and this value has a header and a bunch of fields, or it is just a number. If we scroll down a little bit, we'll see what the difference is. So these 2 macros, isLong and isBlock, are different in the value of the lowest bit. So basically, if the lowest bit of a number is 1, then it's just a number. Otherwise, it's a block. Which means that for integers on 64-bit architecture, there are only 63 bits that can actually carry a value. So, for instance, integer 0 would be encoded as 01, and a bunch of zeros here. Integer 1 would be encoded as 11, and a bunch of zeros here. 2 would be 1, 0, 1, and so on and so forth. Now, if it's a block, then it's something in the heap that has a header. And if we take a look at the structure of the header, we will see basically like the number of words that an object has, a color, that's for GC, and a tag. And tag is 8 bits. So a tag is a value between 0 and 255. But wait a minute, here we have a tag of an int, which is equal to 1000. Well, first of all, int is not a block, so it doesn't have a header, which means its tag is not limited to just 8 bits. But it has to come from somewhere. And here, let's switch into another file, which is obj.c. This is the implementation of methods from obj module. And we'll see that camel obj tag is implemented exactly as we would expect. We just check the lowest bit. If it's 1, it's an int, and we just return 1000. All right, mystery solved. Let's go back to the was it mlvalues.h and try to figure out why we have int64 represented as 3 words with tag 255. For this, we can just use search int64, and here we will just see that int64 is represented as a custom block. A custom block has a custom block tag equal to 255, which matches what we have seen here. This is good. Also, what the documentation says here, we have a custom block which has kind of a pointer to a method suite for functions such as comparison, hashing, etc., followed by raw data. So this gives us exactly 3 words, as we have seen. So mystery solved here. We have another header, custom.h, where this custom operations, this method suite, is defined for int32, int64, and so on. If we look at int64 ops, we see that this is just a structure with a bunch of function pointers inside. So let's say int64 CMP. What it does, it takes the value of both of these int64 values and does your regular comparison. If we take a look at int64 val, this lives inside the mlvalues. And what it does, it takes this data field, here we go, field 1. It takes the data field, casts it into a pointer to int64t, and then dereferences this pointer. This is exactly what we would expect. Switching gears here, let's take a look at some assembly. Starting with something simple, like plus 1 x equal x plus 1. This is the relevant piece of assembly. Our argument is in rex, and then we add 2 to it. You may have a question, why 2? Here we have 1, but 1 is actually encoded as 1, 1, which is 3, and here we have 2. To shed some light, let's add another function. Now this is interesting. We have this instruction called load effective address. And what it does, it takes rex, which is our first argument, then does -1, then plus rbx, which is our second argument. And this kind of gives us a hint as to why we see 2 here rather than 3. Because if we take a look at an example, let's say we have 1 encoded, another one encoded, and then we want to add 2 ones, we should get 2 encoded, right? But the lowest bit is a tag bit, and we don't need to kind of add them up, right? So when we add this value, we get this, and we have an extra 1, which we need to subtract. And this is basically what we see here. So 3 minus 1, which is equal to 2. Cool. So if we take a look at the same example in C, so the same +1 instruction, it also does load effective address, which does RDI first argument +1, and returning this into rex, which is the return register. This is not very much different from just adding 2, right? And if we do the same thing, but let's say for 2 arguments, just plus, yeah, that's pretty much the same. We also use load effective address and so on and so forth. So if we switch back to the editor and take a look at these 2 functions, and basically what they do, they just add +1 in a loop many times. Let's execute them. And we see that, yeah, it's actually, the runtime is pretty much the same. So probably not that much difference in terms of the amount of work done. I guess like the fun part here is that it is important to, like, before you actually make conclusions out of these experiments or benchmarks, it is important to take a look at the generated assembly. Let's say if I change O1 to O2 here and then rerun it, you will see that, hey, C code runs just, in 0 seconds. It is so fast with O2. Is it really the optimizations, right? And the thing is, let me just copy this into the Godbolt. And like with O2, you cannot see a loop or anything like that, while with O1, there is a loop here going on. So yeah, like check your assembly before you run benchmarks and make conclusions out of the runtime. Let's run a similar set of experiments, but for multiplication. So we have 2 programs. We multiply by 86 in a loop a bunch of times. 86 is chosen carefully so that we have a the same multiplication instruction in the generated assembly between C and OCaml version, because otherwise GCC might produce like a bunch of addition and whatnot instead of multiplication. So if we go here and run the program, we will see that C code runs a little bit faster, right? And if we switch to Godbolt and take a look at the generated assembly, we'll see that this is basically one instruction. We multiply by 86. That's pretty much it. We bump the loop variable and we repeat. Now, if we go to the OCaml version, multiplication is actually a bit more involved. So here we do multiplication, the same 86, then we subtract 85, blah, 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 blah. So like a bunch of instructions here. So multiplication with these encoded integers in OCaml is a bit more expensive than with naked integers in C. Actually, another fun story here is that if we run this with O2, instead of 86, we will have 7396. And 7396 is 86 by 86. So basically, the C compiler just unrolled the loop kind of 2 times. However, if we go back to the code here and then compile with O2, it will not actually make, major difference. It's kind of 71 versus 72. So there you have it. Cool. So I think with integers, it's more or less clear. Now let's do the same set of experiments with floats. So when it comes to floats, floats are boxed. So if we ask the same 3 questions for a float value, we will see that float is a block. It has 2 words reachable from it, not 3 as is with int64, and it has a tag of 253. So it is not a custom block, but it's a special type of block specifically for float. So if we go back to the ML values, we will be able to confirm all this, because we have this double tag 253, and we don't need this suite of methods. We know that, you know, the data underneath will be just a double value. So we can kind of save this extra word, but we still have this indirection, right? So we have a block, which is a pointer to a set of words where word is where the actual double is the second word. So if then we take a look at the performance numbers. So let's say we have the same things, but now instead of integers, we use floats for multiplication, and we run the benchmarks. We will see that actually like addition is pretty much the same, like not much difference. When it comes to multiplication, let's run the benchmarks. It is actually, again, the same, unlike with integers where we had a difference between C and OCaml. And the reason for this is that if we take a look at, you just copy this code and paste it into Godbolt. The multiplication here is basically this instruction. And if we do the same for the C version, and let's not do the loop unrolling. Okay. So we have kind of the same multiplication instruction here and here. And then there's the rest of the loop. And the thing is, here we're using kind of the same value over and over again. So I guess the compiler managed to optimize it and not do the boxing and boxing on every single iteration. Now, if we do the same thing, but without inlining of these operations, so let's say we define this function plus f and we say inline never, and then we call it instead of doing, you know, this x plus 86 inline, and we do the same thing in C++, and then we run the same benchmark, and it will take a little while. But yeah, we'll see that the OCaml's version actually runs a lot slower. So now that we have this overhead from function call in C, it runs in 1.2 seconds versus 0.7 seconds. But the OCaml version runs 4 times slower than you know, what we have in C. So there's a lot more going on in OCaml now. And if we switch to the Godbolt, this is the version where we have floating point addition inline. You see we have this kind of tight loop where we just do floating point addition in a register. And I'm not sure why we load this immediate value 107, which is 86 float point. Why we add it every single iteration, but it doesn't seem to harm the perf. But anyhow, so we have this kind of tight loop here. What is going on here is we basically do the unboxing, then we do the floating point addition, and then we put this value back into a box. So we need to do this boxing and unboxing on every single iteration, and this is a lot more a lot slower basically, and it also just requires more memory because instead of just one word you need well, like 3 words, 2 words. So yeah, that's a bit of a bummer if you need to do a lot of floating point operations that are not inside an array. All right, cool. So I guess I would like to finish by getting back to the int64 and just having a look at how the perf compares to just naked ints, naked longs in C. So the same setup, we have this uninlinable function plus 64 that does the addition. We have a similar setup in C. Now let's run the benchmark. and we see that it actually runs quite a bit slower. So with ints, the performance of addition was pretty much the same. Here it is more or less 3 times slower because of the boxing, unboxing, memory interaction, and so on and so forth. So yeah, I guess unless you really need this extra bit of information, ints are a way to go. To sum up, numbers in OCaml are kind of funny. Integers are not 64 bits, but are 63 bits. The lowest bit is always set to 1. The operations are not quite what you would expect to see in the assembly. The floats and int64s are boxed and take up more memory and have worse locality, which is probably not something that will harm you unless you need to do heavy numerics, in which case binding to an existing C library is the way to go. But also it's something that demonstrates that this universal representation of values in OCaml has many benefits, right? It simplifies implementing these polymorphic functions and whatnot, but it also has limitations. And that's why the effort to bring unboxed values into OCaml is so exciting, because it would be just, gorgeous to be able to do all these sorts of algorithms natively into OCaml without having to resort to C. And I guess closing thought is that when I just started thinking about the next video, I was hoping to do something lightweight, a bit less niche than my usual stuff, maybe some type system related easy thing, but it quickly went down this rabbit hole of disassembling programs and looking at C and whatnot. So maybe I should just accept that this is my thing, or not, we'll see. Anyhow, I hope that was interesting. Thanks for watching. See you soon. Peace.